In this lecture, we'll be going over the concept of regularized regression. The reading for this lecture is Chapter 6 in An Introduction to Statistical Learning with Applications in R, titled Linear Model Selection and Regularization. If you have not read this, please pause this recording, go read it, and come back. The three primary topics that we'll be discussing today are ridge regression, LASSO, and elastic net. We begin by discussing ridge regression. All the analysis techniques we'll be discussing in this lecture all are methods of dealing with high dimensionality in your model. In other words, models that are highly flexible. As a reminder, when we talk about dimensionality, we're referring to the relative ratio of n by p, the number of observations versus the number of feature variables you have in your model. As n approaches p, the dimensionality of your model increases, as does its variance. So for example, a one-dimensional feature vector is less flexible than a 15-dimensional vector. As you keep increasing those number of feature variables in your model, you're also increasing its flexibility, which leads to overfitting. So the fundamental question is, how do you select or remove variables in the fitting process itself? In model selection routines like full subset selection or forward or backward stepwise selection, you are forcibly comparing different model configurations. But what if you could do the model selection or the feature selection process in the model fit itself? Well, to think about that, you have to go back to the objective function for linear regression, in this case, ordinary least squares regression. Remember, the goal is to minimize the residual sums of squares. For every observation, you have an error, which is the difference between that observation and the prediction you get based off of your learned model. So if you have p many variables, you're going to get a linear model that predicts every individual yi, and you just sum those together, the squared errors of those together, and that gives you an estimate of the error of your model. And the goal with traditional least squares, as well as really any model fit, is to try to find the parameters that best minimize this residual squared error. So for example, take just a single regression coefficient beta hat j. If you keep changing or tweaking the value of beta hat j, you'll see that the residual square error will change. So as I keep increasing this beta hat, my residual error drops. And then at some point, the residual error in a test case starts to go up. So you want to find in this holdout test residual error, you want to find that minimum of this curve. That convexity, remember, if you meet all the assumptions of ordinary least squares regression, that convexity is easy to find with a closed form solution. If you have non-convexity or local minima in your gradient, then you have to use other methods. But the general idea is to find that lowest point on your error curve. And we went over how in maximum likelihood estimation in the ordinary least squares context, essentially all you're doing is minimizing this residual squared error, which has a lower bound, a pure convexity and a lower bound. That gives you the unique solution to your problem. With regularized regression techniques like ridge regression, what you do is you add complexity to that objective function. Along with trying to minimize the residual squared error, what you're also trying to do is control the size of the regression coefficients themselves. In the case of ridge regression, the goal is to penalize the weak effects so that they have minimal impact on your model. You want to reduce the magnitude of the regression coefficients that don't predict that well so that they have a minimal influence on your model. The objective function for ridge regression looks like this. You've got first your minimized residual squared error, which is the same objective function as what you see in ordinary least squares regression. On top of that, you add this shrinkage penalty here. So you have this lambda hat times the sum of all of your regression coefficients squared. We call this lambda here the sparsity parameter. That determines how sparse your solution is. What this is essentially doing is it's trying to keep your regression coefficients as low as possible by taking that square times this lambda, which means that the larger this lambda, the more that you're going to penalize your regression coefficients in the fit itself. That is the fundamental goal of ridge regression. You just add this shrinkage penalty with the sparsity constraint or the sparsity parameter in on your model fit process itself. Now what that does is as you increase lambda, the overall magnitude of your fit regression coefficient shrinks, and it shrinks in this exponential way. So this is just a hypothetical scenario here showing the magnitude of 5 different regression coefficients, just hypothetical. As I take my lambda from 0, no sparsity constraint, ordinary least squares solution, up to some positive value. And you see that you get this shrinkage of the regression parameters as lambda goes up. And the weakest ones shrink first. So for that particular value of lambda, the weakest ones go towards 0, although they never hit 0, quickly. The stronger parameters, in this case beta 1 and beta 2, take the longest time to converge towards 0. Another way to plot this is by looking at the relative difference between the parameters that you recover from a ridge regression fit, which are beta hat to the r and lambda, minus the values that you get for an ordinary least squares solution. That's what's being plotted here on the x-axis. These are squared differences as well, so you just get a difference in magnitude. What this is really telling us is that if we look at the recovered regression coefficient, shown on the y-axis, the relative difference between the ridge solution and the ordinary least squares solution changes as a squared function. So that when you have a harsher penalty, the values drop off in a squared manner. As at some point you shrink your lambda to the point where there is no sparsity constraint, then your ridge will equal your ordinary least squares solution. So this is just a different way of visualizing that scaling of the regression coefficients that you get with ridge. Now with ridge, you will always return all p predictors. So if you have 5 regression coefficients in your model, you will return with 5 regression coefficients, and some of them will be close to 0, but none of them will actually go to 0. As you increase lambda, you produce weaker or smaller regression coefficients. In this way, ridge manages the bias variance trade-off by reducing the influence of weak predictor variables on your model. Essentially, those variables that are small, like in this example here, the 5th regression coefficient, beta hat 5, end up having the minimal influence because they're so small they effectively don't do anything in your model. But it's important to point out that in this case, ridge does not itself do feature selection. There are no variables that are removed from this model. They're just penalized to the point of being ineffective. Now, the art of doing ridge regression and any sparsity regression, regularized regression technique that we're going to be going over is finding your lambda, finding that sparsity constraint. And it's important to point out that lambda itself is a free parameter. Along with fitting the regression coefficients, you actually also have to fit your lambda or have some way of predetermining lambda. This adds additional steps to the cross-validation procedure that's typically used. Like typical cross-validation, if you want to fit a ridge model, you will first take out a subset of your data to assign as a test set, your final test error set. You'll take out the remaining data and make it a training set. But unlike standard cross-validation in the ordinary least squares context, what you're going to do here is split this training set again into 2 more sets. First, you'll have a tuning set where you will change lambda in a parametric manner. And then you will use that lambda to try to fit regression coefficients. And you'll play with these back and forth to identify first the optimal lambda. Then you'll use that optimal lambda to fit your optimal betas in your training set. And then you will use the results of that fit to evaluate your test error. So it's an additional step of cross-validation. In this case, we have a training set and what are called tuning sets, the tuning of the sparsity parameter, that are required in order to avoid circularity in the regression fits. So you have to fit both lambda and beta together. Let's think about ridge regression in an example context. So for example, let's say that your research question is what brain areas predict reaction times across trials. You're using fMRI to look at responses in the brain while participants are making a simple choice reaction time task to measure the trial-wise responses across all voxels in the brain or all regions in the brain. And your goal is to try to predict reaction time on any given trial, y, as a linear function of the intercept term plus a regression coefficient for every region of interest, r, times the response in that region. So your output is the reaction time in trial t. Your input are the fMRI responses, the bold responses in a particular region on trial t. And your model dimensions here are r is 300 and n is 500. Now you'll see that r is acting as p in the traditional context that I described above. So we have 300 feature variables and 500 observations. This isn't so big that you don't have a unique solution to this problem, but it's a high dimensional problem. It's a highly flexible problem. Now, if we fit our model using ridge regression or ordinary least squares and we compare them, here I'm plotting just a simulated example of what you would see if you fit ordinary least squares versus ridge regression using a particular lambda. And you can see that the ridge regression causes this shrinkage on those regression coefficients. Now, the way this plot is working is actually stacking them on top of each other. So the red bars are in addition to the values that you see on the blue bars. But qualitatively, this gives you the sense of what your regression coefficients will look like as you fit in this hypothetical context. Now, ridge regression itself has its own pros and cons, like any tool. Its advantages are that it manages the bias variance trade-off well when the ratio of p to n is very high, as the example that I did on the previous slide. It's effective more so than ordinary least squares solution, and in contexts where you have some degree of correlation amongst your x's. This provides it to be a better solution for high variance models or high variance modeling contexts. The disadvantage of ridge are that it does not actually do feature selection itself. It doesn't choose regression coefficients or variables. It simply pushes those regression coefficients close to zero. It minimizes their influence on the outcome of the model. But if you use ridge regression and you give it p variables, it will return p regression coefficients just like ordinary least squares. This is in contrast to what happens with subset selection routines, which actually remove variables from your model. Ridge regression and all forms of regularized regression also have the disadvantage that they're not scale invariant. Now, what do I mean by this? Well, in ordinary least squares regression, if I fit a model to a particular x, I'll get a particular regression coefficient. If I scale x by a factor of c, let's say I multiply x by 2, I don't have to refit the model. I could just scale the regression coefficient that I fit also by 2. There's this one-to-one mapping between the magnitude of x and the magnitude of the regression coefficient. So you can scale already fit regression coefficients easily with the ordinary least squares solution. However, because of that nonlinearity in the way the penalty works on the regression fits, you can't do this with ridge. So if you have a collection of regression coefficients and you scale x, you have to refit them. You can't just scale the regression coefficients that you've already fit on the previous version of the model with a different x. Now, Ridge is highly effective in many contexts for trying to manage the bias variance trade-off, but as I said, it doesn't actually select the features that you need in your model in the way that subset selection and stepwise selection routines do. If you want to do feature selection itself in the model selection process, then you have to move to something known as LASSO. LASSO stands for Least Absolute Shrinkage and Selection Operator. It's often just referred to by the acronym LASSO. The goal of LASSO is to remove the weak effects in your model altogether to perform feature selection in the model fit process itself. So the objective function for LASSO looks a lot like the objective function for ridge regression. You'll have first the minimized residual squared error term, the ordinary least squares objective. You also have your shrinkage penalty with its own lambda that needs to be fit. However, unlike the ridge regression, what you're penalizing is the absolute value of the regression coefficient as opposed to the squared value of the regression coefficient. There's the key thing that this subtle difference does. Whenever you square a term, it can never be 0. It will always be slightly more than 0 unless the term itself is 0, which you don't get in regression. If you take the absolute value, it allows for that value to become 0. So LASSO penalizes in a similar way as ridge regression, but what it actually does is it allows for your fit regression coefficients to become 0. It pushes the feature selection process into the overall model fit process itself. If we look at the effect of LASSO on your model fits, you're going to see a similar pattern to what you see on ridge. So as you increase that sparsity parameter, lambda, you'll see that your recovered regression coefficients shrink to 0. And if you look at the relative difference, they scale as this in this nonlinear way. But what happens is that the values actually become 0. Functionally, what that does is it removes those terms from your model. So as I'm increasing lambda in this context, at some point, beta hat 5 disappears from the model. Same with beta hat 3. Same with beta hat 4, then beta hat 2, and then beta hat 1. As I keep increasing that lambda, more and more terms disappear from the model altogether. So unlike ridge, LASSO returns fewer than p predictors with your sparsity constraint being greater than 0. As you increase that sparsity constraint, what you get are more regression coefficients that become 0. Terms get removed from your model more often. So LASSO itself does feature selection in the model fit process by setting those coefficients to 0. What essentially this does is it picks only the strongest. It allows for only selecting those most meaningful factors in your model. There is a degree of symmetry between ridge and LASSO. They might seem marginally different from each other, but there are some meaningful differences, and it helps to think about them in context. For the sake of argument, let's say that my input vector is an identity matrix. So in this case, I have p equals n, so I have as many columns as I have rows. Put another way, I have as many observations as I have predictors. So each observation has a single predictor. Now what this means is that in the ordinary least squares regression context, the unique solution is to set every regression coefficient to its matching observation. If you run the ordinary least squares model where X is the identity matrix, you will recover your regression coefficients as just being the yi's that they're paired to. In contrast with the ridge model, what ends up happening is that the recovered regression coefficient is the paired observation that it's with divided by 1 plus lambda hat. As lambda becomes larger, the value for the recovered regression coefficient is smaller. And it's scaled by this 1 over 1 plus lambda hat. LASSO returns coefficients that are even more complex because you are penalizing by the absolute value of the size of the regression coefficient. What ends up happening is that the regression coefficient you get for LASSO, in the case where the observation is greater than lambda hat over 2, or half of lambda, what you get is the at observation value minus lambda hat over 2. So you just shift your magnitude of your yi by lambda hat over 2. If yi is less than lambda hat over 2, you just add 1/2 lambda to yi. And for cases where the observation absolute value of the observation sits in the range of positive or negative half lambda, you set it to 0. The value of your regression coefficient is 0. Probably helps to visualize this. If we compare the regression coefficients that we recover on the y-axis against the observations that was used to fit them, in the ordinary least squares context, it's just the unity line. It's a perfect diagonal line. In the ridge case, you're scaling the slope of this line by 1 over 1 plus lambda. And in the LASSO case, you're shifting the line plus or minus 1/2 lambda. The slope should be equivalent to ordinary least squares solution. And it should be 0 in the range plus or minus 1/2 lambda. So to take a closer look here, this is the same plot of that LASSO fit in this special context where X is the identity matrix. In the range where Y is plus or minus lambda over 2, everything is 0. So that width of that 0 point in this line, that width of that partition of the line that just sits on 0 is lambda. That's how LASSO does its penalty and does its feature selection. So if we go back to the model, the hypothetical model where you're trying to predict reaction times from responses across a set of brain regions, and we have our data set again where we have 300 regions, 500 observations, Y is the reaction time, and X is the fMRI response in each region on trial J. Unlike the case of ridge, what we're going to see is that there's just going to be a range of regression coefficients that are 0, and then a set of non-zero regression coefficients that present the LASSO. Essentially, what you're just doing is you're not only penalizing the relative magnitude by lambda over 2, you're also removing those weak predictions. So now I have a smaller subset of regions that are predicting reaction time. How do things like LASSO compare to other methods that have been gone over in other lectures, like best subset selection? Well, it turns out that LASSO itself, because it does feature selection, can implement the best subset algorithm with a change in the sparsity penalty. So if you change that sparsity term to being lambda times, instead of the regression coefficient, a specific identity function that returns 1 or 0. So in this case, if the fit of the regression coefficient is non-zero, just return a 1, otherwise 0. What this effectively does is it implements the same algorithm as the full subset selection routine. This returns the exact same result as if you were comparing all possible variants of the model and selecting the model based off of an bias-adjusted information criteria like AIC. In this way, the LASSO or sparsity constraint, if you just change that, what the sparsity constraint is being fit against, to just a binary indicator variable as opposed to the absolute magnitude of the regression coefficient, you will get subset selection. I hope you can start to see that subset selection and regularized regression techniques are all kind of flavors of under a common theme. LASSO will pick the best of any correlated or clustered set of predictor variables. So if you have a set of x that are slightly correlated, what LASSO does is it just picks the best one and it zeroes everybody else out. Whereas Ridge picks the strongest subset of correlated or clustered predictor variables. Ridge will recover the cluster that is meaningfully predictive as opposed to the best representative of that cluster. LASSO, on the other hand, is more conservative than either Ridge or best subset selection. LASSO will not only do a subset selection, but will also penalize the magnitude of the regression coefficients. It leads to a much more conservative model fit. Now, ideally, there would be a way for you to leverage the best of both worlds between Ridge and LASSO. And in fact, there exists such a world. Welcome to Elastic Net. Elastic Net is essentially a little column A, a little column B, a little bit of Ridge, and a little bit of LASSO. The objective function for Elastic Net is a little bit more complicated. You have your minimization of the residual squared error, your ordinary least squares objective function. You have a partial Ridge penalty. So you have now your lambda hat times the square root of the regression coefficients. You also have your partial LASSO penalty. So you still have your lambda times the absolute value of the regression coefficients. But in addition, you notice there's this alpha term. Ridge gets multiplied by alpha. LASSO gets penalized by 1 minus alpha. It's this mixing or balancing parameter. In this case, if you want full Ridge, you set alpha to 1. That zeroes out the LASSO penalty. If you want LASSO, you set alpha to 0. That zeroes out the Ridge penalty. Anything else in between 0 and 1 returns a mixture of LASSO and Ridge. Essentially what this will do is it will do feature selection, like LASSO, but will allow for some clustering in your data. It will allow for some subset of clustered regression coefficients to be recovered. That's the Ridge part. But they will be conservative because their regression coefficients will be penalized. Now pay attention here, because I put a hat over alpha, that mixing parameter, which means that is itself a free parameter that needs to be found as well. You need to now tune alpha and lambda, which adds further complexity to the model fitting routine. So if we follow the cross-validation logic, again, what you do is you set a subset of your data out to become your test set. You build a new training set out of the remainder of the data. A portion of that training set first goes to tuning alpha. You then take that best alpha and you next tune lambda. And then you take that tuned lambda and you fit your regression coefficients that you compare against your test set to evaluate the test error. And you do this for every fold of the cross-validation. So this requires having substantially more data than if you were just going to do either ordinary least squares regression or Ridge or lambda or Ridge or LASSO alone. Doing Elastic Net requires you to have enough observations so that you have reasonable training sets and test sets in order to tune alpha, tune lambda, and fit your betas in a meaningful way. But if you have that enough power in your data set, running Elastic Net will allow for you to choose which is the better way to approach your data, Ridge or LASSO or both. I hope that this lecture has convinced you that regularized regression models like Ridge and LASSO are fast, computationally efficient ways of managing model complexity by implementing feature selection or sparsity constraints in the model fitting process itself. It tries to really work hard to account for the balance of bias and variance in your error so that you can have a powerful enough model that captures variance in your training set and is generalizable to new unseen data in one fell swoop.